Okay, when we try to solve our partial differential equations using the finite difference method, we need to consider the so-called mesh points. So remember our heat equation problem. We have the time derivative, and this is equal to second derivative in space. So we need to represent our solution on a domain of points in space and time. So basically, we will discretize our space domain using delta x. So we have these space steps represented with index n, okay? And for the time, so this is space. For the time points, we are using delta t, and we have this index m. So if you are working out a solution on a domain, let's say A to B, so you will consider starting with time 0. So you have your delta x, so each of these are delta x, and also you have these delta t time steps. We will go forward in time, and we need to evaluate the u values at these points. As we move forward in time, we will get the solution over this whole set of points. Okay, so all these points we call these as the mesh points, and our goal is to get the values of u over these mesh points. Okay, so this is how we will get the solution in the finite difference method. So we will see three types of finite difference methods here. These are called as the explicit, implicit, and we will also take the average of explicit and implicit to get the benefits of, let's say, both methods. So remember our heat equation problem, and we can approximate the time derivative on the left-hand side, you can see, by using the forward time step. So we are taking a forward time step by taking this n plus 1 and taking this difference. And on the right-hand side, we are approximating the second order derivative in space by using this central in space approximation. And this has the error delta x squared, and for the time discretization and approximation of this first order derivative, we have big O delta t. So once we write this, once we approximate our heat equation partial derivatives, then the rest is just rearranging these. So we rearrange and put all the things that we don't know. So the things that we don't know are in terms of the time step n plus 1, because we are going forward in time. So we start with some initial condition and we can go forward in time. And you can notice that these indices with time step m, we can calculate these values starting with the initial condition. So we get this equation 35 here, and what we will do is basically we will start with the initial values, and also at the boundaries we will use the boundary condition, and therefore by going forward in time we can calculate the next point on our mesh. So if you look at here, in order to get to the next time step m plus 1, so if you consider from time step m to m plus 1, essentially we are using three values from time step m, okay, to get the value in time step m plus 1. So this shape, this thing here, basically demonstrates how the solution in the next time step is obtained. So this graph, if you like, this is called as the stencil. Okay, in the finite difference methods, we call this stencil, which is a simple graph that shows how our next values in our solution u is calculated. And also notice that here, actually, for different n values, we can write this similar equation many times. And indeed, this can be compactly represented as a system of linear equations. Okay, so this is why we will explain in the next slide. So here you can see I'm just now switching to the vector notation. So this is actually a vector u, So all the u values are now, we put them together. So starting from, let's say, 1 to n minus 1, and the values at time step m, so these are denoted as um. And notice that the important thing we need to understand is how many equations should we write in the system. So notice that we are starting here with n equals to 1, and if n equals to 1, we have u of 0. But notice that u of 0 values are always coming from the left boundary. And if your small n equals to, let's say, capital N, okay, so that corresponds to n plus 1, so basically that is the right boundary. So if we exclude these boundary points, because boundary points are evaluated from the boundary conditions, we need to write capital N minus 1 number of equations in the system. Okay, so this is the number of equations that we need to solve. And you can see that when we write the first term here, the u0 times alpha term, that is split separately because this is coming from the boundary conditions. And for all the other terms, we can see the inner points are included in this vector. Okay, so this is the size of this vector. So the size of this vector is basically capital N minus 1 times 1. And similarly, the previous time step is the same as well. And this is just representing this system of equations in a more compact way. And basically, you can notice that this is our term g of m, which simply represents the left and right boundaries, and all the other terms here are basically 0. So in the explicit method, there is one constraint, which is on this constant term alpha. So notice that we defined our alpha as the ratio of delta t divided by delta x squared, and if we have a large alpha, which basically you can see from the previous slide, so if the values of our alpha are large, let's say, then you can notice that some errors that we make in the previous time step m is going to be getting larger and larger as we move forward in time. So this means our solution will explode. And in order to avoid such situations, basically this is the so-called stability condition which we need to require in our choice for delta t and delta x values, so that our result, our approximation, will converge to the true solution.